Now, in this video, we will going to take up the simply supported beam. How we can analyze the simply supported beam. We are going to consider a shear force diagram and the bending moment diagram for a simply supported beam with a point load at the midpoint. So that means you have a simply supported beam of A and B which supports at A and B, and then you have a point load which is acting at the midpoint of this beam at the point C, which is acting downwards, which is W, capital W. Now, figure shows a simply supported beam, capital AB, of span length L, carries a point load W at its midspan C. So what are the support reactions? So as the load W is acting at the midspan of the beam, so what will going to be the reactions of the support? The reactions of the support will be equal to RAV will be equal to W by 2 and RBV is also equal to W by 2 because it takes the equal load because the load is acting exactly at the midspan. Therefore, RAV will be equal to RBV, which is equal to W by 2. So as there is no horizontal load, so obviously RAH will be equal to 0. Now, we will try to write the shear force and the bending moment diagram. So to do that, first consider the portion BC now. So we are considering between the portion BC. Consider a section XX at a distance X from B. So what is the SF at this section? So we need to find out what is the SF at this section, which will be equal to. So now by the sign convention, when you are considering the sign convention, here SF is minus negative as the right portion is slides upwards with respect to the left portion. So naturally, so SF towards the left side acting upwards is positive. SF acting towards the right side upwards will going to be negative. So that means S, which will going to be minus W by 2. So SF at this section XX. Similarly, between B and C, SF is constant because as there is no other load is acting between these 2 points. But what is the BM at this section XX now? So between B and C, SF will be equal to minus W by 2. So then we have the bending moment at the section XX. So when you are considering the bending moment at the section XX as this point, so load into the distance. So that will be, since it is a sagging bending moment, so you are going to get positive. So W by 2 into X. So plus W by 2 into X, which will going to be the second equation. You call this as second equation. And the SF at this section, which will be minus W by 2, you call this as the first equation. So the bending moment is positive as the moment of W by 2 taken from the right side of the section XX is counterclockwise direction is positive because it is the sagging bending moment. Now, similarly, when you are considering when X is equal to 0, what happens? Bending moment at the point B will be equal to 0. When X is equal to L by 2, bending moment at the point C will be equal to W by 2 into X. So naturally, it will be W by 2 into L by 2 will be equal to WL by 4 bending moment at the point C. So equation 2 shows that the bending moment follows the equation of a straight line. So that is what. Now when you are considering the portion BC now. So here we have considered the portion BC. Now we will going to consider the portion AC. It is not the portion BC. It should be portion EC now. So consider a section XX at a distance X from the point A. So when you are considering that SF at this section, as we are considering the section XX, as we are considering the section XX here, toward the left side acting upwards is positive by sign convention. So SF at this section will be equal to plus RAV, which will be equal to plus W by 2. So call this equation as 3. So SF is positive, left portion slides upward with respect to the right portion. That is, right portion slides downwards with respect to the left portion, which is in the other words. SF is constant at all sections between A and C. So now, what is between A and C? Shear force, as there is no other load, SF will going to remain the same. That means SF remains constant. That will be equal to plus W by 2. Now BM at the point XX now. When you are considering the BM at the point XX, so again, as towards the left side acting upwards, the beam will going to try to bend in the form of a sagging bending moment. So naturally it will going to become positive, that is load into the perpendicular distance, which will be equal to plus W by 2 into X. So when you are considering this, so the bending moment is positive as the moment of W by 2 taken from the left side of the section XX is clockwise. So when X is equal to 0, so what happens? W by 2 into X will be equal to 0. As X becomes 0, substitute the value of X is 0. So it becomes bending moment at the point A will be equal to 0. So when you are considering the bending moment at the point X is equal to L by 2, so then what happens? W by 2 BM at the point C. So W by 2 into X, when put the value of X is equal to L by 2, so then W by 2 into L by 2 will be equal to WL by 4. So the bending moment at the point C will be equal to WL by 4. So that equation 4 shows that the bending moment follows the equation of a straight line because the power of X will be equal to 1. So that is the reason why it will go to become the straight line. So here, this is how we will going to plot the shear force diagram. So the bending moment at the point B will be equal to shear force diagram. SF at the point B will be equal to minus W by 2. Between B and C, it remains constant as W by 2. BM at the point C, it rises to plus W by 2. Then BM between shear force between C and A, it remains constant, which will be plus W by 2. Now similarly, when you are considering, so SF changes from plus W by 2 to minus W by 2 at C, FJ changes its sign from positive to negative. So naturally, the bending moment at that particular point will going to be the maximum value. So hence the bending moment is maximum at that point, which will be WL by 4. So the maximum bending moment at the point C will be equal to plus W into L by 4. So this is how you will be able to analyze both the shear force diagram and the bending moment diagram for a simply supported beam having a point load acting exactly at the midspan of the simply supported beam. Thank you.